Okay, so something a little bit less mental than perturbative. We'll do a little bit of double copy, then a little bit of world line, and that'll feed straight into the tutorial. Okay, so no backgrounds, no strong fields, nothing like that. As we all know, some endpoint, tree level amplitude and Yang-Mills. You double copy that, and you get some endpoint amplitude, gravity, along with a dilaton and an axion. Right? Okay. So if double copy is something, kind of fundamental to gauge theory and gravity and not just some fluke of doing perturbation theory in vacuum, then it should hold if I expand, or if I do perturbation theory not on vacuum, but on some other background. Right? And how does that work? And the answer is, I don't know. Generally, but there's at least two options, at least. So one option might be the following. Suppose we do some like Yang-Mills scattering in a given background, G mu, for example. Maybe that'll end up double copying to gravity. That's the dilaton plus the axion. All scattering on the same G mu nu. That's an option, right? That might happen. Or maybe the following. Suppose you do Yang-Mills, not in vacuum, but on some color background. Right? Okay, you can do that. And then maybe plus dilaton plus axion. So maybe that double copies to gravity in some background metric, which is somehow related to the background color that you started with. Okay. As I say, you're on the general results. Although I don't know, maybe we'll hear something about this from Sylvia. So what we're going to do is look at some simple examples. See if that tells us anything about what's going on. And we'll start at the level of classical double copy. And a lot of this you'll, I'm sure, be familiar with. But again, some of the PhD students may not be. Go easy. Starting with classical. All right, so long Schwarzschild. This is from Donal and collaborators paper. So Q is some charge, R is exactly what you think it is. That's a vector, and there's some generator, right? So there's Coulomb and Yang-Mills. The non-abelian stuff is just going to sit there, basically. We're not going to be too worried about it. So in some sense, we don't know what the double copy of this is. And in some sense, we absolutely do. Right? Sense that we do, we write this as Q over R 1 x hat, right? It's the unit vector. And the T is just along for the ride. And then if I want to get back to where I started with, I had better do something like plus d mu q mod x. Q mod x. And somewhere I've missed a minus sign and blah blah. Yeah, right. Let's put a minus sign in there. There you go.
The theta function or
No, sorry, that is just that same charge q. Apologies, and that is mod x. I feel like I've done something stupid. Tell me about it. Right. The point being, that's a gauge transformation, so who cares? Throw it away. And that guy has the form of the scalar field multiplied by some vector is null. Zero, right?
Is that a log?
1 over r.
That'd be a log mod x. Yeah, sorry. God. Thank you. Really not on form today. Yeah, okay, sorry, apologies. Okay. That's a gauge transformation. That's really the thing. Okay. What is this now looks like something which is a little bit more in Shield form. So the obvious thing. Just write down a metric where you take that same phi field, 2 copies of that vector. Okay. And of course that is known to be Schwarzschild in some particular coordinates. So a double copy of Coulomb-Schwarzschild, which looks nice. Often this kind of Herschel ansatz is discussed in the context of vacuum solutions of the Einstein equations. Here we've obviously got a source. But the nice thing about this is that the source double copies. So on gauge theory side, the source is just U times L cubed of x, and on gravity side, it's T mu nu of x, and I'm throwing away lots of pre-factors and constants, none of which make too much difference. Okay. Yeah.
What about the gauge part?
What about the?
The gauge part double copied.
Well, this is the thing, right? Well, good question. So, well, then don't look onto this. Does that part double copy?
Not really, I wouldn't say.
This is the thing, right? You don't know what to do with that, right? There's no prescription for taking this and getting.
We don't know of some way in which you could double copy the gauge transformations into the gauge group. And
No, exactly. So it's like this. So 30 Young Mills, and this is some gauge orbit for something, obviously gauge invariant. Then, and this is some Diffie orbit for something which is gauge invariant. Then double copy takes you from some point on this orbit to some other point on that orbit, right? But quite how that point and that point are related.
I would say there are some ways of seeing it. So okay, either you see it at linear level.
Yeah, sure.
But beyond linear, if you use like homotopy algebras, there's
Okay.
a way of seeing it order by order, non-perturbative, but order by order with machinery.
Okay. Cool. Don't ask me. Excellent. All right. Okay. So great. So these classical backgrounds are related by double copy. That's nice. But what about scattering on these backgrounds? Is that also related by the same kind of double copy? Related. Oh, sorry, cut.
Yeah, it's Schwarzschild vacuums throughout. Like if you calculate the TVU,
Yeah.
it's exactly zero.
Singularity of the origin.
Signal of the origin.
Question whether you included the manifold.
Yeah. Right, and it's the same as, I always think of it as being exactly the same as cool. It's a matter everywhere except at a point. But that's the point. Yeah. Come for the physics, stay for the puns. Okay, so this came up as, I think someone asked a question about this yesterday. So what about, kind of amplitudes and observables in these backgrounds? Well, there isn't a statement about, say, how the endpoint amplitude on a Coulomb background double copies to the endpoint amplitude on a Schwarzschild background. We don't know if that works. But if we just go back to perturbation theory for a second and we think about 5-point amplitudes, 1 it's Andres Donald's paper. We know there's a double copy between this guy and the corresponding amplitude in gravity. The probe limit of this guy is the perturbative limit of scattering on Schwarzschild or Coulomb. Right. So there's some connection there going through the probe limit and the perturbative limit. It feels like there's a calculation that you could try and do there to kind of close that circle, maybe.
You try to do it at one loop.
If you try to do it at one loop.
It's drastically different at one loop. You have, for example, in the Young-Mills side, you don't have infrared divergences.
I mean, it's always the issue, right? I mean, you're talking about doing the integrals.
The integrals.
Yeah, the integral's double copy, but doing the loop, the integral, yeah, that'd be different.
Where is it? The computer.
Okay.
From double copy.
Does it work or not?
When it comes to
Integrand.
when it comes to
Yes.
classical solutions, you have the integrated thing. It's not the integral.
Generically, the issue with the double.
Yeah.
You can,
Always different.
for this case, you can double copy the concept charges because the solution is completely solved in terms of that.
Yeah.
So at least for Coulomb, that's what you is talking about. Double copy the charges, which just come from the random. The partial double copy will just be inherited by the charges, and the solution will double copy directly for the 2-point function.
Yeah. Yeah, so if the 2-point function, it works. You could get something promising there, or all right. Moving on. So we're already there at the level of classical solutions, right? And the gauge transformations and the Diffie transformations. There's questions about how it works, and do you have to kind of guess the right gauge to be in order to get it to work, etc. So let's move on. Safe space, plane waves. Right. A plane wave so this is exactly the same expression that we had yesterday. Okay, and if you weren't here yesterday, plane wave has 2 functional degrees of freedom, epsilon of x minus. X minus is a light-like or null coordinate with some associated null vector n. Okay, and again, there's some t. There's some generator which is just floating around. It's not doing anything clever. Okay, let's double copy that because that is a vacuum solution. All right, that's a null vector. That is a scalar which solves the free wave equations. This just screaming out Kerr-Schild. Let's double copy it. Well, there are options. Right? Once again, there are options. So I could just take 2 copies of that null vector n and then the same function. Again, I'm being lazy with factors of the coupling and kappa. And fix them up, right? Well, that's boring, isn't it? That is actually flat. There's no physics interest in that at all.
So the first time is Minkowski.
That's right. Yes, n looks like an eta. You're absolutely right. Yeah. Okay, just one thing you might try, right? You just double copy that bit. And what you get is something which is flat. Dull. So you don't want to do that.
No T there. In the G,
Say again?
in the G part, there no T there.
No, because that is color, right?
Oh, it's color.
Yeah, this is sorry, yeah. This is some color factor. So there's some description. I swap out that color factor for some factor of kappa, which I am not even writing. Yeah. All right, good. Okay, so what else could I do? Well, what I call n and what I call the function in front of n is completely ambiguous, right? I can mix these 2 things up as much as I like. So let's just say, let's try instead. I take 2 copies of n and I take 2 copies of that function. Like that. Okay. Yeah. This is a bit better.
But there is some limit to the ambiguity, right? The identity, because at least for what we know of the curve field double copy, it needs not only be null, but also needs to be geodetic.
Yes, it does.
So you cannot like shuffle around
No,
all you want.
no, in this example, it'll work, but in general, you're absolutely right. Yeah, so I'm ignoring the GDC condition. Yes, good point. Good point. This looks almost like a plane wave. Actually, a PP wave, like the shock wave that we met yesterday, but not impulsive, so they're delta functions. That guy has a source. So this option, I've gone from something which is source free to something which is sourced. Okay. You can pick out the bit which is the plane wave. I just separate this guy into, somewhat unsurprisingly, trace and trace free pieces. Plane wave, and that is, which should look kind of familiar from kind of separation of into, you know, it's just a symmetric trace. This symmetric trace, this bit, that's the trace, that's some kind of dilaton.
I mean, I guess if you worked with Lycon coordinates here, you wouldn't have this nasty thing. Your xj, epsilon j. I think that epsilon was really a helicity epsilon.
It was really helicity epsilon.
Epsilon squares are 0.
Sorry. So my epsilons here are my electric fields. They're polarization directions, really.
They're going to, when you differentiate it, it's going to be, this wants to be a polarization vector, surely, as well, doesn't it?
Yeah, it does want to be a polarization vector.
Okay, so but you're saying I can't make it null because it would be complex. But we do that all the time in amplitudes.
No, nothing to do with it being complex. I can't make it null.
Epsilon, x plus or minus I epsilon y.
Yeah, okay. Fine. Then it would. Yeah, I guess then it would work. But you're right. Then you've got some
Do that all the
absolutely
time.
complex. Yeah, fine. I'm happy to map complex solutions to complex solutions. Fine. If you want real things, then it's a little bit. Yeah. Okay. Good. Yeah. If you complexify stuff and make these things chiral, it's all a lot easier. Everything works. Okay. Relations. So I take this guy instead. xi, xj, h, ij, where h is symmetric and traceless, right? This is a vacuum solution, gauge theory, and there's some t floating around.
So just a question about the source, is it like a scalar, a mathless scalar traveling same speed as the PP wave?
Yes, yeah, the source looks something like n, and then I think you end up with it's either this e squared or derivative of e squared, I can't remember. But yeah, exactly, it's not. Yeah. Good. Ugh. Okay. I'm just consider that guy, gauge theory. So that's symmetric and traceless. These are my transverse coordinates again. There's now two of them. Right, that is exactly the same. It's not a plane wave, it's something else. But that has exactly the same structure as the gravitational plane wave, and I mean exactly the same structure. Right? We had it yesterday. That's a gravitational plane wave. Yeah. So you try and go the opposite direction, think, okay, what is the single copy of a gravitational plane wave? Right, I'll just cover up one of the ends, and that's one possible answer. It's this thing in gauge theory. Right? Not a plane wave. Okay, weird. So
In the single copy, didn't we have to include color as well?
again, you can get, yeah, so there's some factor of kappa or whatever. You can put in a prescription for getting the color out. You get around this factor by if I just multiply this by a generator, I still get that. This level with these simple examples, the color doesn't matter. You just cover it up. All right, well, you include it in your maps. You say, okay, wherever I see E times the generator, that's what I replace with kappa over 2. And you put in whatever you need to get the dimensions, right? It doesn't play any role. So in all the examples I'm writing down, the non-abelian structure doesn't really matter. Okay. There's some kind of like web of connections here where you go from plane waves to PP waves, or you go from plane waves to these things, vortices, in gauge theory. And it's all a bit unsatisfying because you kind of want plane waves to double copy to plane waves, right? They have exactly the same set of symmetry. They have exactly the same functional degrees of freedom. You want them to double copy. Order writing as well, as you can see. So you want plane waves to double copy to plane waves, right? Or rather, you want scattering amplitudes and observables constructed from them to double copy. All right? Maybe we're not so interested in classical solutions, maybe we're more interested in amplitudes. So let's think about amplitudes in plane waves. How we might get a double copy to work with those. And this is taken from papers by Adamo and Mason. Collaborators. All right. We think about some amplitude in Yang-Mills, just calculate it perturbatively. How do we normally do double copy? Well, you write down your amplitude and momentum space, you strip off the delta function, you strip off the color factor. What's left? some kinematic factor over a denominator and you double up the kinematic factor, right? So in some sense, that double copy is working in momentum space in some way. Right. But if we're doing calculations in background, then we don't really have a useful momentum space formulation, right? We have to do everything in position space because we lose momentum conservation. Let's just think about the structure that we get in scattering amplitude in a plane wave background, whether it be in QED or Yang-Mills or in a second gravity. Let's stick with QED and Yang-Mills. And the reason that you can make some progress here is that if you want to write down what a plane wave is in Yang-Mills, it turns out that the color factors are trivial. You want it to have all the symmetries of a plane wave, it's got to live in the Cartan of the gauge group. So it's functionally abelian. Yeah, which is a surprise, but makes things a lot easier and tractable. So, functionally what this means is that scattering amplitudes on a color plane wave look very much like the QED results. Right? Not identical, but very much like it. So what do we have? As in like yesterday, we had some three-dimensional conservation of momentum. We are going to have some unevaluated x minus integrals. One of those every vertex. You will have some, and we're going to look at 3 point just to make life simple. So we've only got one of these, the x minus integrals. Yeah. Let me draw it. That's my attempt at a double line for a gluon. Do it better. You've got some 3-point thing there, and you've got an exponential. If you think back to yesterday, when we were doing the QED calculations, what appeared up in the exponential was stuff like the integral to x minus, photon momentum, classical kinematic momentum, then you had some other dot products down there, right? So normally, so for double copy, you'd strip off a full delta 4, but we don't have that, right? That missing delta function would come from being able to do that integral, but we can't because this thing is some complicated function of x minus. Right? So what do we do instead? Because the symmetry should be the same on both sides, right? We're going from plane waves to plane waves. We should have the same momentum conservation on both sides of this double copy correspondence. So let's say that delta function should just go through. We should get the same delta function on both sides. We're always going to have an unevaluated integral. So that just goes through as well. And in some sense, the phase that you get, you see this just from looking at phase that you get, free theory would just give you, with that integral, your missing delta function. And in some sense, it's universal. It's just this collection of the momenta. And so you can figure out that you should replace this on the gravity side by exactly the same kind of expression. And again, we saw this yesterday. But now where all of these momenta, describe, well, contain interactions with the background. Right? So this is the graviton momentum, which is changing all the time because it's interacting all the time with the background. That's your scalar momentum. So on. Okay, so that looks fairly reasonable. So that's essentially all of the kind of, all the stuff that would reduce to trivial, something trivial in vacuum. And then what's left is this stuff which sits outside the exponential, which I'm not writing down explicitly, but as again, we saw it yesterday. It is some combination of polarization vectors and momentum. So that's the kind of non-trivial part. And here you have to figure out some kind of map which takes you between the Yang-Mills expression and the expression in gravity. And this map, without getting into the details, essentially takes products or single factors the gauge field, the plane wave gauge field in Yang-Mills, into functions of that single 2x2 symmetric traceless matrix, which appears in the action. Right? So you figure out this map for 3 points, go and see if the same map works for 4 points, and it does. 51. 44. Okay. So you can check that this map that you've constructed works. You know, as you go up in a number of points. Of course, it gets increasingly difficult to calculate these things at higher points in backgrounds.
So 5 point is checked or
5 point has not been checked as far as I know. As far as I know. No. Ah.
You have color kinematics duality either.
Yeah.
Would you use color kinematics to higher points to make your life easier?
Yes. No, Sonia's not in the room. I think she might be working on it. Yes, I think so. Yeah. I don't know. They stopped at 4 points and have never gone back. Well, actually, there's a tiny bit of a complication at 2 points. All right. Let's not go to 5 points. Let's go back to 2. So I'll just sketch it. So remember in like the 3-point guys that we saw yesterday, inside this momentum conserving delta function, there was some factor of like, we call it A infinity, it's basically the gauge field, right? Which encoded the memory effect. It looks something like that. So part of these double copy rules, there says when you, after you've applied all the rules, there's like some final thing that says, oh, if there's anything left over, well, it's just a single factor of the gauge field, then you make a replacement which looks a bit like this. So A goes to AI sigma ij xj. Sigma is some deformation tensor in the background. It's just constructed from H. It's not important. The problem is, what's the problem? That says take a function of x, gauge field, and replace it by this function of x minus and x perp. Oh, but this is supposed to be evaluated at infinity and it's appearing inside a delta function. All right. What am I supposed to do there? I can't put x's back into this, right? Doesn't work. So it's not entirely obvious how to double copy the memory effect terms. But the resolution of this is dead simple. Right? You take your delta functions, which appear, you write them back as d3x. Yeah. And then you can apply this map. So once again, this double copy map is working at the level of the integrand. right? Very much in position space, not in momentum space. So 2 points works, 3 point works, 4 point works. Okay. Questions on that bit? All I wanted to take away from this is the fact that the double copy on backgrounds has lots of open questions and lots of things that you can do. All right, looking at simple backgrounds can actually give you kind of tractable. That's all I wanted to take away. Right, to move on. Oh. Right, let's kill this. Okay. The last thing I want to talk about briefly is world line methods. But probably not in the way that you might be hoping. I'm going to talk about this in a very specific context, all right? I'm not interested in the two-body problem at the minute. For this part, I want to talk just about pair production. Pair creation. There's one thing that the world line approach is really good for. Right? So we talk about amplitudes all the time. These are obviously exclusive quantities, right? We choose our final state, and then we calculate the probability of getting that final state. Sometimes it's much easier to calculate inclusive quantities. Sometimes. So let's imagine starting in the vacuum. I turn on some external field, DVD, Young Mills. I turn on some curvature somehow. Doesn't matter what I do. Okay, and I calculate the amplitude for staying in vacuums. This is the vacuum persistence. Well, I'm just going to write that as e to the I gamma, just to give it a symbol. And then what you find generically is that the probability to stay in vacuum, right, to start with vacuum and to end up with nothing of interest at all. Well, this is just e to the I gamma, e to the minus I gamma. Right, I'm not saying anything about whether gamma is real or imaginary, obviously. Okay, so that is e to the imaginary part of gamma, if I've got the signs right. That gamma happens to develop an imaginary part, yeah, and this is not 0. Sorry, this is not 1. What's the point? It's obviously not 0, right? It's not 1, which means there's a probability for you not in a vacuum, something has happened. Of course, what that something is that the field that you turned on turned out not to be stable to quantum effects, and those quantum effects produce pairs. Okay. So the probability that you produce pairs is just 1 minus that. Right? 1 pair or 2 pairs or 3 pairs or 4 with any momentum spectrum, whatever you like, inclusive. Yeah. You just need 1 minus the probability that you didn't. Okay. Typically, these things are small. Say again?
Why are they pairs?
Oh, because I'm thinking about QED. Sorry. And then you produce pairs, charge conservation. Generically, stuff. Produce stuff.
Yeah. Even in QED, produce 4 objects that are correlated, like not just 2 pairs. That's what is down by an order or something.
It's down by an order, but you can do it. Yeah. There's, it's not on the reference list. There are papers by Francois Gély, who talks about all these kind of correlations in particle production. And yeah, beyond leading order, it gets quite intricate. Yeah, it's cool. I'll send them to you later, remind me. Okay. So normally, and again with my QED hat on, certainly terrestrially, you know, the number of pairs that we can produce by turning on a really strong electric field is quite small, vanishingly small. So we can expand this exponential and basically twice the imaginary part of this guy is what we want to calculate. Okay, and the world line method gives you a way of doing this. So this is the world line prescription for calculating that thing. Again, let me write it down and then I'll tell you what it means. Right. So what the world line says is integrate some classical action, which I'll tell you, I'll write down in a second. So I'll give you some classical action, then you integrate over all possible periodic trajectories. It's periodic because this thing gamma that we're calculating is basically that diagram. Put an arrow on that if you want something spiraling around. Yeah. T here is basically the length of the trajectory. So you also integrate over all possible lengths, and there's a 1/t there. As soon as you see that, you know that you're talking about one. Right? If you're familiar with world line calculations, then you're doing tree level stuff. That T is not. Yeah, it's there, you're doing one. Okay, so let me tell you what the action is. The relevant action just describes a classical particle coupled to whatever field you're interested in, which might produce pairs. So QED, again, scalar QED really. The action, you've got m squared T over 2 plus the integral of some kinetic term, and then you've got coupling. Yeah.
Why the word line and not some optical theorem?
Because the word line is the simplest way of calculating.
It's simple. It's
Really simple.
simpler than the optical theorem.
Oh God, yeah. Yeah, I'll show you explicitly. Yeah, it's really simple. Okay, so I choose some electromagnetic field. I switch it on. I'm interested in creating pairs from it. There's my field. That's the action. This is just the classical action, right? It couples a classical particle to a given field. Work out the equations of motion, Lorentz force equation, right? I'm saying that because we'll need it in a second. So this is all integrated. Everything is a function of some proper time tau. X dot mu tau. Yeah. And then gravity, well, what could that be? You get m squared T over 2, no surprises there. And then I've got a particle in a background metric. So I've got something like g mu nu, x dot mu, no surprises there. And then you get this annoying factor of minus t over 8 times the Rishi scalar. Right. You expect that bit, right? It's the obvious generalization of that bit. You take, you vary this action, you get the equations of motion. It's the geodesic equation. Yeah. What is that bit doing there? That's there because gravity is a mess, right? And you have to and you get divergences all over the place and blah blah blah, and you have ghosts. Short answer: that is there. So the answers which come out of the world line approach are the same as the answers that come out of the Feynman diagram approach. That's it. It's discussed quite nicely in, where is it? think 94. Kafka and collaborators. Possibly some people in this group. There we go. Yes, good. You discuss it nicely in this paper. And it's a very old story, right, which goes back to DeWitt about why this term is here. Okay. Right. So I'm telling you that to calculate this probability, you need to do a path integral. It's not a lot of fun, right? You might think, oh, can I just do some amplitude calculation, get the optical theorem? What I want to show you is that there's a dead easy way to do this calculation approximately to capture all the really interesting stuff. So the simplest way of doing this calculation physics hat very firmly on. Let's do everything in a standard point approximation. Do everything in a saddle point approximation, and this is what you get. I think I had a minus sign. Doesn't matter. The imaginary part of gamma, the exponential of the classical action, evaluated on a solution of the classical equations of motion. This is just what falls out of doing the integrals in a saddle point approximation. So let's just think about what that really means. I'm just going to do the QED calculation, for example. So you solve the Lorentz force equation in your chosen background. Not hard if you choose a nice background. Here's the trick. There's some factor of P floating around, which I've missed, isn't there? That's got a T in it, so there's going to be a factor of T there. Apologies, that's going to be important. Okay, solve that. The path integral that we started with had periodic boundary conditions, so this guy had better have periodic boundary conditions. And that is the key step. I mean, as an instruction for how to calculate something, solve the classical equation of motion, subject to these boundary conditions, doesn't get much easier, right, in general. So, what I'm going to do, is stop there, if that's all right.
Yep.
Yeah.